Hi everyone, welcome to my YouTube channel. Today we will be discussing about Dirac delta function. This is another example of continuous basis like plane waves. We can write any wave function of the wave function space as a linear combination of Dirac delta function, but this is a continuous one, so we have to write those in form of integration. So let's say psi r naught r, this is a function which is given by delta r minus r naught, which is the Dirac delta function, and the function looks like this: a sharp infinite spike at the position r equals to r naught and 0 everywhere. We know from the property of Dirac delta function that it picks the value of the function where the spike present, that is, if we write f a equals to f of x delta x minus a dx, here the spike is at x equals to a. Similarly, psi r can be written as psi r naught delta r minus r naught d3 r naught. We are integrating on the variable r naught and the spike is present at r, so the integration will give the function at that point, that is r. Similarly, psi r naught can be written as psi r delta r minus r naught d3 r. Here the variable is r and r naught is the position of the spike, and we know that delta r minus r naught is same as delta r naught minus r. These are even functions. Now if we use this equation psi r naught r in these equations, we get psi r equals to minus infinity to infinity integration of psi r naught r d3 r naught, and psi r naught equals to integration minus infinity to infinity psi r naught r star d3 r, where these two functions are same, the psi r naught and psi r naught star, because we know these are Dirac delta functions and the complex conjugate of the Dirac delta function is the function itself. We are just writing star because we want to describe psi r naught as the coefficient of expansion, and we know that the coefficient of expansion is given by the scalar product of the corresponding basis with the wave function psi. That's why we are writing psi r naught star. So every wave function in the wave function space can be expanded in terms of psi r naught. So they form a basis and the expansion coefficient is given by psi r naught, and the index is r naught, which varies continuously from minus infinity to infinity, and r naught is playing the same role as p in case of plane waves, where p varied from minus infinity to plus infinity. Now check the normalization and closure relation. So the scalar product of psi r naught with psi r naught prime is delta r naught prime minus r naught, which is the normalization condition, and we have already seen in the previous class of plane waves that the normalization condition for continuous basis changes to Dirac delta function instead of Kronecker delta function. That's the difference between discrete and continuous basis, and closure relation is given by the scalar product of psi r naught r prime with psi r naught r, and which is given by delta r minus r prime, which is the same as the discrete case. So what are the key differences? The difference is that so I changes to r naught, where r naught is a continuous parameter but I is discrete parameter. It can only have integer values, but r naught can have any values, and the summation over I changes to integration with respect to the parameter r naught. And we have already said that the Kronecker delta changes to Dirac delta function. These are the main three differences between discrete and continuous basis. So let's compute or formulate a generalized continuous orthonormal basis. Let's say W alpha r is a generalized orthonormal basis. So we know that this has to satisfy the normalization condition. So the scalar product of W alpha prime with W alpha is the Dirac delta function delta alpha minus alpha prime. Similarly, the closure relation is integration of W alpha star r prime into W alpha r d alpha is delta r minus r prime. Let's say we can write a wave function psi r as psi r prime delta r minus r prime d3 r prime. Here r prime is the dummy index or parameter, and we know that this integration is going to give psi r. This is a very famous property of Dirac delta function. And let's say we are using the closure relation in this equation. We write this whole integration part instead of delta r minus r prime in this equation. So we get this equation, and then we write the integration d3 r prime W alpha star r prime psi r prime together inside a square bracket, and we are defining the term inside this square bracket as C alpha. So psi can be written as integration of d alpha C alpha W alpha r, where C alpha is the term inside this square bracket, which is nothing but the scalar product of W alpha with the wave function psi. Let's say we choose two wave function and expand them in terms of continuous basis W. So phi is d alpha B alpha W alpha, and psi is d alpha prime C alpha prime W alpha prime. We are just changing the parameter from alpha to alpha prime to avoid any confusion when we are using both of them inside an integration. So the scalar product of phi with psi is integration d3r, then phi star into psi. So instead of phi star I am writing this integration d alpha B star W star, and this integration is as it is. Then I am choosing d3r W alpha star and W alpha prime together inside the square bracket, and we have the rest of the thing as it is. And we know that this relation inside this square bracket is the normalization relation for continuous basis. So instead of this we can write delta alpha minus alpha prime, and we have now a double integral, and the integral variables are alpha and alpha prime. So let's integrate first with respect to the integral variable alpha prime, and we know that this is the famous Dirac delta function integration, and we know that this integration will give the value of the function at the position of the spike, and the spike is at alpha. So the integration will give B star alpha C alpha, and we already have integration over d alpha. So the scalar product is given by integration d alpha b star alpha c alpha. In case of discrete basis, we had summation over I bi star ci, but as this is a continuous basis, instead of summation we have to use the integration, and after the calculation we can see that our prediction is matching with our calculations. Similarly, the norm square, that is the scalar product of psi with itself, is integration c alpha square d alpha. So all the formulas of discrete basis can be applied here, only you have to do some changes in notation. So you have to change the discrete index from I to a continuous variable alpha, the summation I to an integration d alpha, and Kronecker delta to Dirac delta function. So I have made a comparison table so that you can understand the discrete and continuous basis very clearly. So we had our discrete basis as ui, and we had our continuous basis w alpha, but the difference is that the I is a discrete index like 1, 2, 3 etc., but alpha is a parameter which varies from minus infinity to infinity continuously. So orthonormalization condition for discrete basis is the scalar product of ui with uj is delta ij, but in case of continuous basis the scalar product is not a Kronecker delta, it's a Dirac delta function, and the closure relation is the same, but instead of summation we have to use an integration over the variable alpha. So the expansion of wave function in case of discrete basis is just summation over I ci ui, where ui are the discrete basis, but in case of continuous basis we have the expansion coefficient c alpha and the basis is w alpha, and instead of summation we have this integration over d alpha. So component of the wave function is given by the scalar product of the corresponding basis with the wave function, and this is same for both continuous and discrete basis. Similarly, the scalar product for discrete basis is summation over I bi star ci, but in case of continuous basis we have integration of d alpha b star c. Similarly, the square of the norm for discrete basis is summation over I ci square, but in case of continuous basis it's the integration d alpha c alpha square. So that's all for today. So if you enjoyed my video, please subscribe and share it. See you in the next lecture. Thank you.